Welcome, AI developers and architects. Today, we are unlocking a superpower in agentic development, time travel. Specifically, we will master how to debug complex LLM workflows by rewinding graph history in LangGraph. Let's dive in and bend time. Let's kick things off by defining what we mean by time travel. When you execute a standard script, if it fails at step 10, it crashes and the memory is wiped. You have to start over. In LangGraph, because we use a checkpointer like memory saver or Postgres saver, the framework takes a complete snapshot of your agent's state at every single node execution. Time travel is the ability to browse this history of past states, replay them, or even branch off from them. Why is this a superpower? Because LLMs are inherently non-deterministic. If your agent hallucinates a bad API call on step 5 of a complex workflow, time travel lets you pause, look at the exact state before the hallucination, and understand exactly what went wrong. We are moving from a black box execution model to a fully auditable, reversible thread. Take a look at this flowchart to visualize the concept. The agent executes step 1, step 2, and step 3, saving a snapshot after each. At step 4, it makes an error or a bad choice, represented by the red node. Instead of restarting the entire process from step 1 and wasting tokens, the developer uses time travel to follow the dotted rewind line directly back to the green node at step 2, seamlessly inspecting the state exactly as it was at that moment. Why should you adopt rewinding as your primary debugging strategy? First and foremost is cost efficiency. If your agent has already performed 5 expensive web searches and summarized 20 pages, rerunning that from scratch just to debug step 6 is a massive waste of API tokens. Second, LLM bugs are notoriously hard to reproduce. If the model hallucinates a weird JSON format, restarting might just give you a correct format by chance, hiding the bug. By rewinding the history, you preserve that exact problematic state. You can freeze time, inspect the LLM's exact reasoning, fix the flawed plan, and resume. It also opens up incredible experimentation. You can rewind to a specific decision node and try out 3 different system prompts to see which one guides the agent down the most optimal path, starting from the exact same intermediate context. This diagram contrasts our debugging strategies. On the left, the traditional restart from scratch approach leads to high token costs and lost state context. On the right, the rewind history approach offers a vastly superior developer experience. By utilizing checkpoints, you achieve 0 token waste and exact state preservation, allowing you to isolate and squash bugs with surgical precision. Let's look under the hood to see how this is architected in LangGraph. The foundation relies on 2 critical identifiers. First is the thread ID. This identifies the specific execution run or user conversation. It groups all the snapshots into one timeline. Second is the checkpoint ID. This is generated after every single superstep or node execution, capturing the exact state at that microsecond. When we want to time travel, we combine these 2 into a config dictionary. By passing this config to the graph, we tell the framework exactly which timeline and which moment in time we want to access. The primary tool for this is the getStateHistory config method. When you call this, LangGraph reaches into the database and returns an iterator of all past states. Crucially, these states are sorted in reverse chronological order, meaning the most recent state is always the first item returned, making it easy to step backward. Follow the sequence diagram to understand the data retrieval. The developer requests the state history for a specific thread ID. LangGraph queries the memory saver checkpointer, fetching all checkpoints associated with that thread. The memory store returns the array of checkpoints, sorted from the most recent, CP3, back to the oldest, CP1. The developer can then iterate through this list and inspect the exact state stored inside CP2. Let's look at the actual Python code required to replay the past. Our goal is to force the graph to re-execute starting from a specific, historical checkpoint. Step 1, we fetch the history by calling list graph.getStateHistory config. We convert it to a list so we can easily index into it. Step 2, we identify the past state we want. Remember, index 0 is the current state, index 1 is the previous step, and index 2 is 2 steps back. Step 3 is the secret sauce. We extract the specific configuration dictionary attached to that historical state by calling history.config. This config contains the exact thread ID and the historical checkpoint ID. Finally, step 4, we replay the execution. We call graph.invoke none, past config. By passing none as the input, We are telling LangGraph not to add any new messages, but simply to resume execution identically from the precise moment captured in that historical config. This class diagram highlights the objects involved in replaying history. The state snapshot object returned by the history method contains the actual data values, the next node to be executed, and importantly, the config object. This config safely holds the thread ID and the unique checkpoint ID. To time travel, we simply extract this config and pass it directly into the graph.invoke method. Replaying the exact same history is useful for observation, but to actually debug, we must change the past. If the LLM hallucinated, replaying the same state will just reproduce the hallucination. We need to create an alternate timeline. The concept here is forking. We inject a new state or override a flawed response at a specific historical checkpoint. First, you retrieve the target historical config, just like before. But instead of invoking it, we use the graph.updateState method. We pass in our past config and then provide a state update, for example, replacing the bad LLM message with a manually corrected message. Under the hood, LangGraph doesn't overwrite the original history. It creates a brand new forked checkpoint branching off from that moment. You then resume execution using the config of this newly created fork, allowing the agent to continue down a repaired, successful path. This timeline diagram visualizes the forking process. The original execution goes from step 1, generates a bad LLM output at step 2, and results in a graph crash at step 3. Using time travel, the developer goes back to step 1 and applies an update state call. This creates the green alternate timeline at step 2b, featuring the corrected output, which successfully leads to step 3b. We have successfully rewritten history to debug our agent. Let's apply this to a highly critical real-time use case, debugging a multi-agent software development system. Imagine you have a planner agent that researches documentation, followed by a coder agent that writes a Python script. During execution, the coder hallucinates a non-existent API parameter. The execution node runs the code and throws a fatal error. If you use a standard rerun, the planner wastes precious minutes and API costs replanning, and, because of LLM variants, the coder might generate a completely different, unrelated bug. This makes debugging a nightmare. Enter time travel. The developer fetches the state history, rewinds to the exact checkpoint immediately before the coder generated the bad code. They use update state to inject a strict constraint into the state do, not use parameter x, and then resume execution. The coder generates the correct code, the execution succeeds, and the bug is squashed instantly with complete deterministic control. Follow the debug flow in this diagram. The planner hands off to the coder, which hallucinates, leading to a crash at the execution node. The developer inspects the crash, then rewinds time via the dotted line back to the coder node. By injecting a corrected state, the coder makes a second attempt, flowing into the execution node perfectly and terminating at the green success node. Total time saved, massive. As we conclude, we must acknowledge the architectural trade-offs of time travel. Saving the entire application state, including huge arrays of messages and retrieved documents at every single node, consumes significant database storage. While in-memory saver is fantastic for rapid local debugging, you must deploy a persistent backend like Postgres Saver for production. To manage the storage overhead, it is a best practice to implement strict time-to-live (TTL) policies on your checkpoint databases, clearing out old threads automatically. Mastering the ability to browse, rewind, and fork graph history is the definitive skill that separates amateur prompt engineers from true agentic software architects. It gives you the power to debug the non-deterministic. Thank you for joining this masterclass. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Keep building, and see you next time. Our final architectural diagram highlights the deployment strategy. Your time travel architecture splits between development using the lightweight in-memory saver and production using the robust Postgres saver. Because production leads to rapid storage growth, you must proactively manage it. Branching down, we manage this growth by implementing TTL policies to delete old runs and state compression to keep the database lean and performant.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.